What is the topic of today's webinar? Well, today we're going to be discussing AI within the wireless and the aerodef industries, some of the applications of AI, um, and whether or not it's the right time to apply AI in these industries. Before we dive into the actual presentation, I'd like to give a quick introduction about the presenters. For today's session, we're going to have two presenters, namely myself, Darshan Mikan. I'm a solutions engineer at Optimum Solutions. I have a degree in mechanical engineering from WITS. I currently work within the digital engineering sector, servicing clients within the aerodef, wireless, automotive, and smart mining and manufacturing industries. And I have a keen interest in developing AI, data science, and data analytics solutions for the digital engineering and smart mining industries. I'll now hand over to Nadia.
Good morning, everyone. My name is Nadia. I'm an application engineer. I'm based all the way in Glasgow, Scotland. And I support our customers in our standards-based solutions. I also dabble in some of the AI and the application of AI to wireless. And I work with customers both from aerodef and from KC Industries. And I also have a background in the HDL design for DSP applications and communications applications.
Thank you, Nadia. The agenda for today's meeting will be we're going to do an introduction to AI for wireless, where we discuss is it the right time to implement AI solutions to the wireless industry. We're going to give an introduction to AI, the different types of AI that are available, and we're also going to give some examples for how AI is currently being used in the wireless industry. I'm then going to discuss the design workflow to give you an idea of the steps required when developing an AI solution. So we'll talk about data preparation, AI modeling, simulation, and test and deployment. And lastly, Nadia will be giving a demonstration of the design workflow using a spectrum sensing and deep learning example. So let's jump right into it. The first question is it time for incorporating AI solutions into your wireless capabilities? And the short answer for that question is we believe that it is. We have seen that there's an exponential increase in the algorithmic complexity of wireless systems. The environment in which they are being applied to has also become a lot more complex. And therefore, the products that you guys are developing have to be more complex. They require more parameters to characterize the system performance. And the traditional methods that are used to tune these parameters and characterize the system performance still can be used, but they have become lengthy and more challenging to implement. And hence, AI has provided a way to do this in a more efficient manner. And it's currently shown promising results in the signal processing domains for image, audio, and speech, and so forth. In addition to that, for the 3GPP release 18, there has been regulations and policies and standards put into place for AI within 5G. And that basically shows that they are anticipating AI to be ingrained within the 5G and beyond standards. So we do definitely believe that AI is going to be part of the wireless industry in the future. So how can AI help? Well, AI can contribute in network simplification, improve system performance, and spectral efficiency. Some additional applications for AI within the wireless industry has been it's being used for spectrum sensing and signal classification. It's being used for device identification, so to identify whether a certain device is an intruder into the system, is it mimicking another device and trying to be an imposter. It's been used for digital pre-distortion, beam management, channel estimation. It's been used for localization and positioning and transceiver design. So these are some of the use cases that we've seen and MathWorks have seen AI being used within the wireless industry. But what are some of the name players that have, bigger named companies that are using AI currently? Well, one example is Mitsubishi Electric. They have been using deep learning to do digital pre-distortion for nonlinear compensation. And they have used MathWorks tools for the entire workflow. They started off with using the communication toolbox to develop signals that they can use to train their network on and acquire different types of signals. They then use the deep learning toolbox to develop the AI model or the deep neural network, and they use Simulink to run the simulations and test their AI model and determine its performance. They also used additional tools such as HDL Coder to then take the AI model that they developed and generate convert it into HDL code, which they then deployed onto an FPGA. So what this shows is that larger companies do see the benefit of AI within wireless, and they also have been using the tools that MathWorks provides because they see a lot of value and potential in it. So now I'm going to give you an introduction to AI and the different types of AI in case you are not familiar with the terms and topics. So where did AI start? Well, the idea of AI started in around the 1950s, and it was essentially just people trying to see if they can mimic human intelligence on a computer. And it started with basic ideas such as using if statements. Then, as time progressed and computers became faster and more advanced and processors became faster, AI evolved into machine learning, where we try to apply statistical methods to enable machines to learn tasks from data without explicit programming. So the need for human intervention became less. Then again, as time progressed and technology advanced, machine learning morphed into deep learning or advanced into deep learning, where we have the idea of neural nets. And the difference between machine learning and deep learning is the fact that deep learning requires less or minimal human interaction. And we'll discuss that in detail a little later. So let's look at machine learning and the different types of machine learning that can be performed. Machine learning can be broken down into three main camps. The first is supervised learning. Unsupervised learning. Unsupervised learning requires no labeled data. It's generally used to develop additional insights into the data by performing things such as clustering. So, for example, if you look at the data set on the right, this is just a 2D plot of the data set, but you can see that there is a clear definition between two camps of this data set. So you can use clustering to see if there's similarities or extreme differences between the data. Now, this is just a 2D representation, but this data might exist in a 5-dimensional space. And that will be very difficult for humans to uh, identify those similarities and differences. But for unsupervised learning, there's techniques in place when performing clustering that allows it to determine these differences. The second type of machine learning is supervised learning. Now, supervised learning requires labeled data. That means it's a data set that contains labeled data and of what the features are, what the responses are. And for the responses, supervised learning is predominantly used to do things where predictions are involved and required. So things such as classification and regression, where the algorithm can make a prediction and then compare its prediction to some labeled data to determine its performance. So where does deep learning fit into this entire workflow? Well, deep learning is a subset of machine learning and particularly supervised learning. The difference between deep learning and supervised learning is an idea called feature extraction. Feature extraction is essentially the ability to, or it's the ability to identify things within the data that can be used to classify whatever you're trying to classify. So if I have to give an example, if you're trying to create an AI model that will take in images and identify whether there's a vehicle in the image, um, with feature extraction would be identifying certain parts of a vehicle that can be used or identifies that can be used to identify that this is a vehicle. Now, the difference with machine or supervised learning and deep learning is that in deep learning, the identification of feature extraction is automatic, and in supervised learning, it's manual. So in supervised learning, a human will have to go through some of the data and physically identify that, okay, here, this is labeled that these are tires, this is a windshield, this is a rear view mirror, or so forth. And tell the algorithm that these are important features to identify that this is a vehicle. Deep learning does that process automatically. It learns what it believes are important features for identifying what a vehicle would be. The only thing that you need to keep in mind about deep learning is that it requires large amounts of data. The third camp of machine learning is reinforcement learning. Reinforcement learning is best suited for controllers because it teaches controllers how to make appropriate decisions and actions. So a controller will make an action, it'll pass it to an environment or plant that's being modeled. The plant and the environment will react to the action that it's provided and provide a response back to the controller. The controller will then use reinforcement learning to identify whether the response, whether its action had a positive effect on the environment or a negative effect. And from there, it will learn what actions are good to take and which actions are not good to take. Great. So now that we understand a little bit about the three camps of machine learning, how can these three concepts be applied within the wireless industry? Well, unsupervised learning can be used for small cell clustering, device-to-device user clustering, and anomaly or intrusion detection. Supervised learning can be used for channel estimation, spectrum sensing, beam selection, antenna design, just to name a few. And reinforcement learning, as I mentioned, is most suitable for controller design, and therefore it can be used for things such as resource allocation, transmission power control problems, and so forth. Okay, so now that we have a basic understanding of AI, the different types of AI, and how they can be applied to the wireless industry, let's take a look at the steps required for developing an AI solution. So the AI workflow consists of four predominant steps. That is data preparation, AI modeling, simulation and test, and deployment. Data preparation focuses on acquiring data, either real life data, or if you don't have real life data, generating synthetic data. It then takes the data and transforms it into a usable format that can be passed to the AI model. AI modeling focuses on designing the actual AI algorithm and training it to improve performance. Once you have a trained model that you are satisfied with, you can run it through simulation and test. This is where you take brand new data that the model has never seen and you pass it to the AI algorithm and you visualize or you monitor its performance. Is it able to make the correct predictions or not? Because training an AI model on training data can actually just the model can just learn specific patterns within the training data and it might not be able to perform well on new data. So you have to do simulation and testing. And lastly, once you have a workable AI solution, you can then deploy it onto embedded devices, enterprise systems, and edge and cloud systems. So the question I want to pose to you, and I believe there's a poll question in the chat, is what is the most important step in this process? And I'll give you some time to think about this. While you're thinking about that, I want to just discuss a few of the toolboxes that MathWorks provides to make developing AI solutions easier. So when it comes to data preparation, we have toolboxes such as the instrumentation control toolbox and communication toolbox that allows you to acquire real-life data or generate synthetic data. That data then can be passed into MATLAB for pre-processing, and then it can be passed to Simulink to run through a simulation. When it comes to AI modeling, um, there is the statistics and machine learning, deep learning, and reinforcement learning toolboxes. These toolboxes provide functions, apps, examples, and so forth that make it easier to develop AI models and allow you to learn the best of practices on how to develop AI models. For simulation and test, we have tools such as Simscape, which is our physical modeling environment that allows you to create models of physical systems so that you can test your algorithm against it or on that plant without having to test it on a real world system. Once you've generated your model, you can run it through simulation using Simulink, and you can use Simulink test to be able to compare the model's outputs with the expected outputs to validate performance. And lastly, When it comes to deployment, we have a number of different coder tools such as HDL coder, PLC coder, embedded coder, Simulink and MATLAB coder, which allows you to take the model you developed and automatically convert that into usable code such as HDL code or C++ code that can be deployed onto hardware, enterprise systems, and so forth. So going back to the question that I asked, what is the most important step, or what do you think is the most important step when it comes to the AI workflow? And I see 90% of you answered data preparation, and that would be 100% correct. Data preparation is the most important step or component for a successful AI solution. And the reason is you need to have good data because it forms the foundation, and garbage in will um, result in garbage out. Because if you train your model on data that is of not good quality or doesn't capture the entire um, use cases, all the use cases, it won't be able to, when it sees new data, it won't be able to make accurate predictions. So how do you acquire this data? Well, currently, some of you might already have a lot of data available, good quality data that you can use to train your models against, and that's really good. But what if you don't have sufficient good quality data, or what if you haven't even started collecting data yet? Are you now bound and not allowed to create AI solutions? And the simple answer to that is no, because there are tools such as the phase array toolbox and the communication toolbox that allows you to generate um, synthetic data that you can use to train your models against. So you can generate this synthetic data, you can then add noise onto that, and you can pass that into your algorithm for training. And one of the ways, or one of the tools that we have available for you to do this is the waveform generator app. So I'm going to quickly jump into MATLAB and show you this app. So what you're seeing right now is the MATLAB IDE. And if you look on the top, there's a tab for apps. If you select apps, there, depending on the license that you have in the toolboxes that you've purchased, you'll have access to all these additional apps which are made to specifically make it easier for you to perform certain workflows. So we're going to open up this wireless waveform generator app. And essentially, sorry, I forgot to mention what we're doing in this example. We're trying to create an AI model that's able to identify between 5G signals and LTE signals. So for that, we're going to need to generate some 5G signal data, well, data for 5G signals. So if we open up this wireless waveform generator app, what you're greeted with is this. This is what the app looks like. And on the app, you'll see that you can generate a number of different types of signals, whether it be simple sine waves or Bluetooth signal. You can also generate 5G signals. So if we select this downlink FCR, it opens it will allow you to change the different parameters for the signal depending on your specifications. Once you're happy with the specifications that you've put in, you can select generate, and the app will automatically generate this 5G signal for you. And there it is on the right. It also provides some additional data about the signal that it just generated. Once you're happy with the signal, what you can do is you can export it. So you can export the signal as a variable to the workspace, or alternatively, you can export it as a MATLAB script. So if I do that, it'll take me to MATLAB. And one of the benefits of doing this is that, as you can see, the script has all the different specifications for the signal explicitly stated. So you can actually run a parameter sweep on this, where in each iteration it changes a different specification slightly, and it generates a new signal. So by running a parameter sweep on this, you'll be able to generate a large amount of data extremely quickly. Okay, so back to the presentation. Okay, so now I've just shown you the waveform generator app, and you've seen how to generate some synthetic data. The thing is, you don't only have to, MATLAB doesn't just have the waveform generator app to develop synthetic data. You can also get data from other sources. One of the ways is you can acquire live data directly into MATLAB using hardware such as low-cost SDRs, and these are the ones that are supported by MathWorks, along with other commercial RF signal generators and spectrum analyzers. The other way that you could use this is, let's just say you have generated um, a signal using the waveform generator app, but now you want to increase the fidelity of the signal by applying some real life noise. Well, what you could do is you can use the instrumentation control toolbox to do this. So in MATLAB, you can use the waveform generator app to generate your signal. Then using the instrument control toolbox, you can connect MATLAB up to devices such as an RF signal generator, and you can send that 5G signal that you generated to the RF signal generator. The RF signal generator will then broadcast the signal or radiate it out into the open air, which can then be picked up by another piece of hardware called a spectrum analyzer. Now, the signal that the spectrum analyzer has picked up will be your 5G signal along with additional noise that it's picked up from the environment. And you can use the instrument control toolbox again to bring that signal back into MATLAB. And now you have a signal that has some real life noise with it that you can use to train on your algorithm. I'm now going to hand over to Nadia, who's going to take us through a demonstration of data preparation.
Fantastic. Thank you, Darshan. You set the stage very nicely here because what I'm going to demonstrate is, in the context of these 4 steps, data preparation, AI training the model, validation, and so on, how this applies to this example. So first of all, how do you get to this example? If you have communications toolbox and open the documentation, you can see that there is a category there that is just for deep learning and wireless, and you can open and see all the examples that exist today that you saw on one of the earlier slides. And of course, we add more examples as we speak to customers about their applications and what they're trying to do. So this example, the one I'm walking you through, is the one for spectrum sensing. This is relevant for both AeroDef and KC customers in some ways. It's important to understand what is in your spectrum before you maybe go and use a radar or something else, or maybe you wish to identify a kind of unwanted signal in the spectrum. Likewise, for example, standards compliance, or how to say spectrum compliance purposes, you may wish to test that your broadcaster or your cellular transmitter is in fact transmitting within the band that they're allowed. So there are many different applications here. The benefit is that you don't have to be an expert, you don't have to decode any of these signals to identify what they are. So generating this training data, Darshan very nicely set up the stage here that we can use synthetic data and we can sweep over many parameters. So that's what we are doing here. We were choosing various parameters to sweep over. That requires obviously some knowledge of the standard and some knowledge of, well, what will the operators actually use here. So we can go, the search space can be very, very large, or we can use some knowledge to kind of try to make it smaller. And so if we flick in MATLAB to the actual example, I've just put in the slide so you can kind of follow the first step here. We will sweep over these parameters. Now, we're not doing this sweep today because it's a lot of data. It could be gigabytes of data. I've already downloaded all of the data. It's already shipping with this example. But if we were to go and train this data, we will find that here we can leverage some power force of some parallelization to generate our sweeps faster. And we can see that we can generate a 5G NR signal and an LTE signal. If we were to go into for example, the NR function here, we will find the exact same NR waveform generator function that is called from the app. Now, what does this example work on? It actually works on spectrograms. So if we just flick down a little bit to the bottom just to see what we're looking at, this is what it actually operates from. So we may generate baseband signals in the end, but actually we want to use spectrograms in the end. So we generate this data, or it's downloaded it already, and this is what it actually looks like. So we have a lot of the math files, the baseband data, and also PNGs for the actual spectrogram. So this is what one of our spectrograms for LTE would look like. We sweep over various noise and so on. So we have about 900 frames of each one. You can see it's taking up a lot of space here, but we can let this run overnight and then observe our results. We can see that also we have moved the data around the band here so that we don't bias the training. Finally, it uses another kind of image processing in order to extract the features, and that is called semantic segmentation. So what semantic segmentation means, it's a typical image processing technique, not just applied to wireless, it's just any images, whereby we will it's kind of like blob analysis. We will say, this blob is LTE pixels, this blob is just noise, the kind of pink, and this cyan is just the NR. So in advance, these spectrograms we saw earlier would be passed through a some signal and image processing to label the pixels. So we can then obtain some statistics on our data, and we can see that we have a relatively large number of pixels which are labeled as noise. At 0.1, this is frequency, 0.1, 10% of the time we have LT, 20% we have NR. So we can get an understanding of what is our training data like, what is the quality like. From here, I won't spoil it, but we can kind of see that it's possible that we may bias our AI because we may have more NR than LT. So we need to maybe iterate over this. And this is obviously a process that we iterate over many, many times using kind of human insight. So far we've got our data ready, and the next step we'll look at a bit later is how do we train our network. So back to you, Darshan.
Thank you so much, Nadia. And thanks for the great demonstration on developing data preparation. Okay, so the next step in the process is AI modeling. For this, MathWorks has 3 different toolboxes available. That is machine learning toolbox, deep learning toolbox, and the reinforcement learning toolbox. And although you can go ahead and develop your own machine learning algorithms and that by yourself, it will take a significant amount of time. These toolboxes allow you will provide algorithms, pre-built models, functions, and so forth for you that will simplify the workflow of developing these algorithms. So for example, when it comes to machine learning, there's algorithms to develop things such as decision trees. Deep learning, there's algorithms for developing CNNs and long short-term LSTM networks. There is reinforcement learning algorithms such as DQN, where it will set up the agent and critique for you. There is regression algorithms, clustering algorithms, and predictive maintenance algorithms as well, if you are interested in doing predictive maintenance. And of course, there's also Bayesian optimization algorithms that can be used to iterate through the training process and um, basically optimize the hyperparameters of the AI algorithm to improve performance. An additional benefit of these toolboxes is that they give you access to these pre-built models. So for example, these image classification models, these are very well-known image classification models such as GoogleNet and ResNet. And you might be thinking, what is the benefit of having access to these image classification models when they haven't been trained on my data? Well, there's this concept called transfer learning, and transfer learning is the process of taking a very well-known model that has already been trained for certain things, so in this case, images, and you can provide new images to it that it has never seen or been trained on, and retrain the model on those images. And the benefit of doing it that way is that the development time or the training time for for developing, for example, an image classification model becomes greatly reduced because the architecture and infrastructure for the image classification model has already been created by, for example, ResNet and GoogleNet. And you're just reusing that and retraining it on your data. If you are new to the topic of AI, machine learning, and so forth, I would encourage you to look at some of the reference examples. For example, there's examples on object detection, semantic segmentation, signal and speech processing, and so forth. It's a great way to ramp up on the concepts because the examples take you through step by step how to develop an AI algorithm and some of the considerations that you might need to make. So, having access to these toolboxes also provides you access to things such as the apps that come along with these toolboxes. And the apps are there to accelerate your AI modeling process and to decrease the amount of time it takes to develop these AI algorithms. So there's two main apps that are available, and that is the Deep Network Designer app and the Experiment Manager app. Before I jump into explaining these apps, I'd just like to explain what a deep neural network is briefly, just for those who are not familiar with it. So I've put a summary of it as in this image on the top left, and the different circles in this image represent nodes, and a column of these nodes represent a layer. So neural nets are built up with layers, and each layer does a different task in the classification or prediction of whatever you're trying to achieve. The things that are existent in all neural nets are the input layer, which is the layer that takes in input data. So if you're, and the number of nodes in this layer depends on how many inputs you are supplying to the model. Then there's the output layer, and the output layer is what will provide the prediction or the classification, and the number of nodes are dependent on how many things you're trying to predict. So if you want to try and predict 5 different things, there'll be 5 nodes, and so forth. And between the input and output layers where the magic happens, and this is done by the hidden layers. And hidden layers can contain things like activation layers, ReLU layers, and so forth. And the hidden layers are the ones that need to be trained, and the hyperparameters need to be tuned in order to improve the accuracy of the model. Now, the typical way of designing a neural net like this is to do it programmatically. So you would physically write code that says, okay, this is the input layer and this is the parameters that it contains. These are the hidden layers and these are the parameters that it contains, and so forth. But this might be quite intimidating for novice users, and hence there's the Deep Network Designer app, which allows you to develop neural networks in a low-code format. So similar to Simulink, it essentially has all these different blocks on the left for different input layers, convolution layers, hidden layers, and so forth, that you can just drag and drop into the workspace, and then you can use signal lines to connect the different blocks together. You can then select on a specific block, such as this one, and you can change some of the parameters on the right to suit your model. Once you're happy with the model that you've created, one of the benefits and big advantages of this app is the Analyze button. You can select Analyze, and it'll automatically analyze the model that you just created, and it'll notify you if it identifies or thinks that there's going to be any runtime errors, if there's something that's not adding up with the models, with the parameters, and so forth. But if there are no errors and you're happy with the model and the architecture that's been developed, you can go ahead and you can export this neural net directly into MATLAB, and it'll be ready for use. Okay. The second app is the Experiment Manager app, and the Experiment Manager app allows you to essentially perform the hyperparameter tuning a lot faster. So instead of having to manually go through the code and change parameters that you want to test for, and then identify with the performance of the model and note it down, there's the Experiment Manager app, which allows you to select the type of optimization you want to do. In this case, they are using Bayesian optimization. It allows you to put in the parameters that you want to iterate over. So for example, In this case, we want to iterate over the mini batch size between a range of 10 and 40. And we've added a few more there. And it allows you to essentially just, in an easy way, in a nice graphical user interface, apply all of these experiments that you want to run on the model. And then you can go ahead and train it, and it will run through all the different variations based on your inputs and tell you what the training accuracy, training loss, and so forth is. And from there, you can select the best performing one and you'll get the parameters for that model. So the last thing to consider when developing an AI solution, or a question that you might have in your mind right now, is what learning technique is best for my application? So once you've selected whether you're going to do unsupervised learning, supervised learning, and so forth, the next step is to determine, do you need to perform machine learning? Well, basically just regular machine learning, or do you need to do deep learning? And the answer for this question will be based on four different things: data set size, domain knowledge, compute resources, and the fourth one, which I like to add in, is interpretability. So if you have a very large data set size, but not a lot of domain knowledge, you would need to then perform deep learning. Whereas if you have less data available, but you have a large domain knowledge, you would be able to perform machine learning. But like I mentioned before, there's this fourth one that I like to add in, which is interpretability. And this is industry and application specific. Some industries require that when you apply AI, it needs to be interpretable, meaning that if you put in this input, you need to be able to determine that it's going to come out and determine and explain why it's making a specific prediction. Now, deep learning doesn't allow you to do that because it's generally just a black box and it's difficult to explain and understand how the neural networks are making predictions. Machine learning, on the other hand, is more interpretable because, for example, when you're developing decision trees, you can take a new piece of data and you can follow the decision tree and all the decisions down because it can display how it's making the splits in the data. And you can follow that down and determine exactly what the prediction is going to be. So once you've selected what type of technique is best for your application, you then go into the training and testing phase. So I've summarized the workflow up until the testing stage and verification stage on the slide. So the first thing you need to do is take the data that you have and split it into training data and testing data. For the training data, you'll take the data, you'll perform some sort of transformation on it. So like Nadia mentioned, you can take uh, audio data and so forth and transform it into an image. And the reason we do that is because, for example, it's a common technique because there is very well-known image classification models. So you can apply one of those like ResNet onto the images and you can start performing transfer learning to speed up that development process. So once you've trained the network and you've trained the hyperparameters, you end up with a trained model. But the trained model has only been trained on the training data. In order to really validate its performance, you need to pass in unseen data to this model. And that's where the testing data comes in. The testing data, you take it and you perform the same transformations on it as you did with the training data, and then you feed that into this trained model that you just created. You take the predictions from the trained model and you identify or you compare it to what the expected results are, and you can determine whether or not it's performing as expected or how well it's performing. And that sums up the AI workflow up until testing and validation. I'm now going to hand over to Nadia to take us through a demonstration of AI modeling and testing.
Thanks very much, Darshan. So let's recap back on our original example for spectrum sensing, where we got to. We ended up using the NR waveform generator to generate a lot of spectrograms. So what we've ended up here in our data is we have a lot of LT spectrograms with various noise profiles. You can see here some are very hard to distinguish, some are a little bit easier. We have the same thing with the 5G NR data. We also have combined spectrograms of both LT and NR. So to the naked eye, you may not, you can see we have variability in noise, in bandwidth here. To the naked eye, you don't know which is which. You cannot say if you're not a really domain expert to be able to recognize like this. So now we have this data. What can we do? We've also done in the background semantic segmentation, whereby we've labeled the pixels, whichever ones are LT, whichever ones are 5G, whichever ones are noise. So what choices do we have here? If we are a AI expert, we can decide to build our own neural network, maybe take from the literature or something like this. But one technique that is very useful for novices is actually to perform transfer learning on a already existing network that has been trained on certain images. For example, ResNet. There is ResNet, there is GooglyNet, there is various ones that have their trade-offs. But let's imagine that we are going to do transfer learning on ResNet 50, and we're going to use that as our base network. Now, there's some balancing of classes. Remember earlier I showed you that we have a little bit of mismatching of the amount of kind of data for each category here. But we're going to do a little bit of balancing of these classes to improve our results. Finally, Darshan showed you the experiment manager. This is, if you like, the programmatic API to set up the training, how to say, all the parameters you can choose when you're doing your training. The experiment manager will sweep over these parameters. Here, let's say we have already maybe gone through the experiment manager, we've chosen one set and we're happy with that. So we're staying with this. So, you can choose the batch size, max epochs, the type of algorithm for training, and so on and so forth. So we're not going to train this now, obviously, because as you can imagine, this takes some time. We've already trained this network in the past, so we can just load it in. So we have it. We can have it. Now, next step is the testing. How do we know how well our network performed? So, of course, it's very important to take one step at a time. And first, we want to train with, again, 5G and LTE signals, again, synthetic, but ones that the network never saw. So completely new ones. Now, there was a step earlier on where we divided up our data. I think I missed to say it last time, but there's a step that we did in the before where we divided up 80% of our images to be used for training and 20% for validation. So 20% of these images this network never saw. We're going to go back and try to train with test with synthetic data. So we'll see how good our accuracy was. Well, we train on 900, we test with 900 images, we get about 88%. We can look at the confusion, matrix here and see what we got. I can skip ahead to oh, there we go. So we can see that, these are synthetic images. We've already trained it with synthetic. It's a little bit like cheating, but it's a good first step to evaluate that nothing has gone wrong. We can see that LT is a little bit poorer, NR is a bit better, noise is the best. That actually kind of matches the profile earlier, where we kind of thought that we're probably biasing it a bit well for noise and for 5G, but not so good for LT. So again, like I said, this is iterative process. So another thing we can investigate that is popular is called the intersection over the union. It's the ratio of correctly classified pixels to the total number of ground truth and predicted pixels. This is kind of some statistical analysis we can do, and from that we can choose to do additional rebalancing of the data that we use to train. Finally, we can see that, some of the low SNR frames, like you saw yourself, they can barely see anything in them. So actually, they may be just biasing our data without helping in any way. So we can choose to just remove some of these. We can generate some junk data. We notice that we have junk data. Let's remove this junk data because it's not helping us. It's making things worse. And this is the kind of analysis that's happening here, and kind of picking some data out that's not helping and trying to make this better. Finally, finally we can kind of then see whether we're doing a little bit better with this. Let me see if there should be another matrix here. Oh no, there doesn't seem to be. Yeah, right. So okay, so we will rebalance our training data. We can try training again. We can test again and see how we are doing. But the real truth now comes whether a network that has been trained with synthetic images can perform just as well on real data that was captured using, for example, SDR, like Pluto, something off the shelf. This is now real data that came from actual operator. How well can it perform? So what we have done here is we have captured some results, and we have done the same operations. You know, we have done a spectrogram, and then we can evaluate how well the signal labels have been here. So we have a few captures like this. And we can also overlay the result with some kind of drawing to tell us, you know, from here to here, this is the LT. So if I just switch back to the complete write-up that shows everything, we can have a look at the true signal labels that we expect, which is we expect that this is labeled as LT, this is labeled as NR, and so on. And this is what we actually receive from the network, which isn't too bad, you know. And again, we can look at the performance and try to make it better. And finally, this is kind of a fancy overlay to show us where is the LT and where is the NR. And to test over the air, it's quite simple. We can use Adam Pluto device, and we can actually continuously keep running this SDR to keep capturing over the air and doing the classification, doing the spectrogram, and then sending it into the AI to give us some results. So this has all of the actual nice results here in the images. So you can take a look at that and then see what you think. That's me. Back to you, Darshan.
Thank you so much, Nadia. Yeah, so then to basically round out, the last step in the AI process is deployment. So now that you have a working AI model, that you're happy with its performance, the next step is to actually deploy this onto some device so that you can start using it in the field. And MathWorks supports deploying it onto embedded hardware such as HDL, PLCs, GPUs, and so forth. And we have coder products like an HDL coder, PLC coder, that will take your models and automatically generate code from it, whether it be HDL code, PLC code, or CUDA code, and so forth. There's also MATLAB compiler if you want to generate or basically compile the algorithm into a standalone executable, a MATLAB web app, an Excel add-in, a Docker container, and so forth. And if you want to deploy this onto enterprise systems, there is MATLAB compiler SDK that allows you to deploy it onto C or C++ DLLs, Java, Python, and so forth. So the last thing I have to share is that AI can be a very daunting task and developing AI solutions can be quite daunting. But we do have some self-paced online training and online examples that you can use, and I do encourage you to go through to learn about AI, the different methodologies, and how to develop an AI solution. These are also free for anyone to use. So if you go onto Google and you type MATLAB self-paced online training, you'll be able to access short courses such as machine learning on ramp, deep learning on ramp, and reinforcement learning on ramp. If you would like to do a more instructor-led and advanced and intermediate courses, please reach out to me. We do have courses available that you can do. There's also online examples, so like the one that Nadia showed, you can go through that. It takes you through the steps and the processes involved in developing AI solutions, and you can use those as a baseline for your own solutions. Thank you so much for attending today. I'll now open up the floor for any questions. I think let me start. There is a question. There's a few questions in the chat. I see. Okay, so there's one
I think
about, yes. Sorry, Nadia.
I've been answering as I've been going, but
Okay,
feel free to
perfect.
read them out if you wish. Yeah.
Okay, perfect. I actually haven't read the answers, but the first one is basically it's about AI supervised learning versus unsupervised learning. Should you just be using supervised learning? I think in most cases, supervised learning is preferred because you're generally trying to make a prediction from the data. But you can use unsupervised learning to do clustering to identify or learn more about your data and then identify good data, bad data, and get rid of junk data. It is a possible workflow. Um, yeah, I guess if the answers, if Nadia has answered these questions,
Yeah,
if
I
something
think
isn't clear, yeah.
the same person gave a follow-up though, because I asked for a bit more clarification on
Okay.
w- learning using clustering just not would that not take care of the junk data? And there was a
Mhm.
follow-up. I asked a bit more to elaborate, and they said the thought would be that you must gather relevant data, avoid preparing the data so that you can remove the bias that I would have as a modeling agent. The assumption is that unsupervised learning with relevant data from a live network, then the model would learn and gain further insights.
I don't know if there's any follow-up questions to Nadia's answers. Is it clear? Feel free to unmute and we can have a discussion about it.
I think that both approaches are really correct based on the person what they said.
Mhm.
And it really depends on how good the data is. With unsupervised, sure, I think you can use it, but it can also end up in the wrong direction as well because it is completely unsupervised at that point. We usually ask people to try it and see what happens. And it's an exploratory research type of activity rather than a one correct answer. But I think if you know something about your data and if your gut feeling is that you should try the approach, for example, supervised, I think it's best to try it out and see what happens. There's so many parameters to tune and knobs to turn that it can be quite a long exploratory cycle to get there. The good thing is that with the tools, you just hit the button and you just do it again and again and again, as long as you
Yeah,
need to.
I definitely agree with you. From my experience, developing AI solutions is more of an iterative process. And I guess that's where the benefit of some of the MathWorks tools come into play because you can, like you said, it's generally low code formats. There's these apps available, so you can actually go through the process without spending too much time on it, and you can get some sort of insight on whether or not you should go down that rabbit hole or not. Yeah.
Mm. The real value of MATLAB is its ability to process large amounts of data. Basically, data. This is all a big data problem, and MATLAB I think really shines in when it comes to large amounts of data, and of course using parallelization to process large amounts of data in parallel.
Yeah. One thing to mention though is although we are speaking about MATLAB a lot, you don't exclusively have to use MATLAB. We do understand that some people prefer working with Python libraries such as TensorFlow and that, and MATLAB does also plug and play with those. So once you've developed that, you can connect it up and bring it into MATLAB to do um, simulation and testing with Simulink, for example, if you prefer to use Simulink for a simulation environment then. Okay. Are there any questions from the audience? If you aren't able to ask it now or you think of something later on, please feel free to give me an email, send me an email. I'll put my email address in the chat for everyone to available. Okay. Seems like there aren't any questions. So thank you so much, everyone, for attending and for your time. I hope this session was insightful and gave you some ideas on how to apply AI within the wireless and aerodrive industries. We would be happy to collaborate with you on any projects or help you identify, do an evaluation of whether you should be taking the route of AI for your projects. So please do feel free to reach out to us as well. Thank you, everyone. Have a good day further.
Thank you. Take care.